Okay, Jessica, this is going to be the second video. I don't know what's going on with Zoom tonight if you can't get on using the link I sent you. This is my personal meeting room link, so if you can get on, that's great. If not, I'm very unhappy that we can't actually talk. But the issue is that you watch the previous video as well, and we'll take it from there. I don't know what else to say at this point, other than it's just apparently not going to cooperate with us tonight. It's been one of those weeks for me too, believe me. So here's something I need to talk to you about. We may end up doing more of this class by Zoom. I may have to go back to Northern Virginia in the next few days. My father is dying in hospice, and I need to go back and take care of a lot of details. I'll probably be gone for a week. Since it's just the two of us in this class now, Kyle, unfortunately, his mother is quite ill, and he is out of town. We can do this probably by Zoom. We'll have to just make arrangements as to when good times will be. I will keep you informed of my situation with respect to the potential for having to travel as well. We can meet by Zoom. Clearly, in-class exercises are going to be out. I'm just going to pull them out of the grade book, so don't worry about that. There won't be any harm done in this class. But the thing that I want to do is just keep this going. We were talking about z-scores, and z-scores have a lot to do with the ratio of the data point, the difference between the data point and the mean, and divided by the standard deviation. So what you do, a z-score is simply a number of standard deviations away from the mean. The z-scores are normalized in that fashion to the normal distribution. So let's go back to the Triola text. Let's do a new share and go back to here, or what am I looking at? Yeah, here. This is what I want. So we want to go back here to the concept of the standard deviation. And once again, we're going here. Standard deviations are, this is a plot of a normal curve. A large enough data set collected in the proper manner should give us a something that very close to a normal distribution. Large enough is a relative term, but usually we're talking about several hundred, if not thousands, of data points. There's a mean that is, we call that sort of the 0 point. In a normal distribution, the mean is considered 0. A standard deviation is 1. So the one standard deviation on either side of the mean, remember, is 68% of the data. 2 standard deviations are 95% of the data. Anything outside of 2 standard deviations away from the norm is considered unlikely. It's a 5% or less chance, basically. If we think about that, if 95% of our data are within plus or minus 2 standard deviations, then there's a 5% chance that a new data point will fall outside that, and 5% is considered unlikely. So to make it even more unlikely, 99.7% fall within 3 standard deviations. So the z-score is simply a number of standard deviations minus or plus in a positive direction, meaning to the right of the median, or a negative direction, meaning to the, or a negative meaning to the left of the median. Anything more than 2 standard deviations is considered outside the is considered improbable. Excuse me, is considered improbable. So that is why we talk about this. This is an empirical rule, and it basically applies to these standard data sets. So make assumptions when you're asked to calculate a z-score that it is going to be a standard distribution, a standard normal distribution of data. Chebyshev's theorem allows us to include things that do not have a normal bell-shaped result. However, we're not going to worry about that. So for all of our work here, we're going to assume normal distribution. So let's go back and let's take a look at a couple of other things. Let's just quickly. All right. I'm going to pause the recording for a moment while I look something up. Okay, now I've gone to chapter 6 of the Triola book, and this is page 247 of chapter 6, the standard normal distribution. For here, we're talking about a large enough data set. The mean is 0 and the standard deviation is 1. The total area under this curve is also equal to 1, so that any fraction of this area is less than 1. One of the things that you're going to be asked about in your let's just be sure that that's right. Let's go back to your problem set here. We are asked find the probability of the reading. So this is going to be out of chapter 6. Standard normal, find the area if there's a mean of 40 and a standard deviation of 5. All you're doing basically is finding the area of anything greater. It's going to be brought back to normalized, back to the normalized value of sort of scaling it down to the 0 and 1. So a mean of 40 and a standard deviation of 5. We'll get to that, to how you do that in just a couple of seconds in the Triola text. So let's go back there. So probability of finding a standard a sort of normal distribution is unfortunately, I'm trying to find out if we have what we need here to actually look at this. I think I'm looking at seeing if we have the Z tables. Do we? Okay. Do we have the appendices is my problem. And so this is not the full text. Let's just see if we can find out if we have any. No, we do not. All right. Standard normal distribution. I'm going to have to scan and send you some information on the calculations, but we'll take a look at this. So the standard normal distribution here, if we go back, let's look at this. We look at the data, standard normal distribution. Again, we talked about that, and the standard normal distribution is represented by this bell-shaped curve. Not easy to manually figure things. There's a table. I'm going to send you a copy of the table in Appendix A. I've got it. I'll have to scan it and send it to you. Using that table, the table will allow you to look at a z-score and calculate a probability. So let me tell you how that works. And I can only read out of a copy that I have here that won't show very well. But what we have is we have standard z values that range from 0. Obviously, 0 is right on the median here, because we calculate z by subtracting the. Hang on, please. I'm going to have to pause this again. Okay, here we are again. Where were we? Finding probabilities. Let's just take a look. If this is a normalized area of 1, and if the mean is 0, we have exactly half of the data will lie on the negative side, in other words, below 0, and exactly half the data will reside, above this level, above to the right of the median, of the mean. So that means that a random chosen data point has a 50% probability of being to the left of the mean. That's all that means. So we can use these ratios. We can calculate out here to the -3 position. There is if we look at that, there is according to this schedule, there is a 0.13% chance of the data of a piece of any random data that is chosen or a new point being added. There's a 0.13% chance that it will be more than 3 standard deviations away. How do I know that? From a table I'm going to send you that I would have given you here in class tonight. So we can do this and actually calculate this using these tables that you're going to receive. So there is a way of doing that. So the probability here, you don't have a stat disk and you don't have table 2. So I'm going to, or A2, until I email it to you. So what we can do is put that off. But what I will show you here is if we looked at the table and we calculated a z-score of 1.27. How do we calculate that? We divide the distance away, the difference between the data point and the mean. So it's the data point minus the mean, okay? The data point minus the mean divided by the standard deviation. That tells us how many standard deviations it is away. Here's an example of what is of this table A2 and how to read it. If our z-score is 1.27, that's positive. That means, first off, a positive number means that the data point is to the left of the mean in the normal distribution. So we read this table, the z-score. You can see here the z-score is down here. It goes from 0, where it's a 50% probability that it will be to the left, because 50% of the data are to the left. So it's 1.2. So we read down the table to 1.2. We've calculated 1.27, so we read over and intercalate over here. If we go over here, this is 1.20, this is 1.21, etc. Get over here, 0.8980. So the area to the right of that table, of that z-score, is 89.8% of the total area of the curve. Okay, so we can calculate that. Remember, all we have to do, if we go back over here to our assignment, we've got 32, find the area if there is a mean of 40 and a standard deviation of 5. So we've got 32 minus 40 is going to give us a minus 8 divided by 5, the standard deviation. So 8 divided by 5 is 1.6, so this is minus 1.6. When we look at our table, minus 1.6 is 5.48%, 0.0548. So there are two things. We know that this is not an unlikely result, because it is greater than a 5% probability. But the area, meaning the area to the left, okay, is going to be 5.48%. Okay, so we have we have that. So that's the area, the standard normal distribution area. Okay, find the probability. And the probability and the area are the same thing. So what we have is, if in that first one, if the reading, okay, we have, assume the measurements are given, have a mean of 0 and a standard deviation of 1. This is problem 2. Less than 2.02, so that's a positive number. So we look for 2.02 and we get 0.9783. So 97.83%. We also know that that means that that there is only a few percent that's not there. So 97.83% is of the area under the curve of that probability is there. So the probability of the number being less than that is 97 point, what did I say, 97.83%. That is a probability. So if we just get another random point, there is a 97.83% chance that it will be have a z-score of less than 2.02. Okay. Now, greater than 1.45 is going to be, if we look at that, so we look at 1.45, and that is 92.65%. Okay. That's going to be 92.65% will be less than that. So the greater is that. So it's going to be 1 minus 0.9251, or about 7.5%. Okay. When we're looking at between, what we do is we just take the difference between 1.8, the area of 1.8 and 2.1. The area of 1.8 is 0.9641. The area of 2.1 is 0.9821. So we just take the difference between that, and that's the probability of the data point being between those two. So you'll get that when you get the table. Let's go back to the table again. Go back to the textbook. We're going to be there. We're going to be done shortly. So so let's just take a look. This data here, we've got a z-score of 1.27. So this is taken from some bone density test results. The probability that the person will have a bone density less than 1.27 is 0.898. Okay, and that's shown here in this shaded region. Another way to interpret as to conclude that 89.8 people have a bone density below 1.27. Okay, so we can use the tables for to calculate the area. And again, if we look at this area here, we've got a z value of -1. If the z-score is minus 0.1, reading off the table, we find the probability of a bone density of greater than that is the area to the right of minus 0.1 is 0.84, blah, blah, blah. So the area to the left is the difference, or 0.1587. So there is a 15.87% chance of someone with a bone density lower than a z-score of 1.0. So we have, again, an interpretation, this probability and the area of the normal curve, because 89 or 84.13% of the area of the curve is above a z-score of -1. So this is how we look at probabilities in this arena. Now, if we are looking at a slightly different kind of problem, and not looking at something that is a normalized curve with a mean of 0 and a standard deviation of 1. What we do is we look at a slightly different set of calculations here, in which we look at the data. We're not going to look at non-standard deviations. What we're going to do here is try to get to a problem. Okay. So if the mean is this number, 63, this is height, standard deviation of height of women. 63.8 inches is the standard height, and so that is, the mean is going to be a z of 0 to a z-score using a formula here, where we simply divide. Again, the z-score is calculated by dividing the difference between the mean and the data point, dividing it by the standard deviation. So a woman who is 70 inches tall has a z-score of 2.38. So again, we can determine using the table the z-score of 2.38. I'm going to read this off of my copy, which you will get, is going to be 0.9913. So that is 99.13% of women will be below 70 inches in height, which means the difference between that and 1 are 0.0087 or 87 hundredths of 1% are going to be 70 inches or higher. So all we do is normalize the scale by dividing the difference between the mean and the data point by the, so we subtract the data point from the mean, the difference between them. So we have the data point, we subtract the mean, we get a number. It's either positive or negative, it doesn't matter, because these things are mirrored on either side of the mean. So if we calculate that z-score, it's the same thing as if we used the standard normal distribution. So anyway, that's as much as we're doing this week. I'm very sorry you can't make it. What I've got is I'll have two videos for you. I'll label them video 1 and video 2. As I said, we don't know what's going to happen with my father. I had to take a short break because my brother-in-law called me basically to tell me there's no new news. But we have no idea what's going to happen with my father, other than he will die. He is on hospice and is not going to leave there until he's carried out to the funeral home. So if that happens in the next few days, I will be on the East Coast and we will have class by Zoom. I will let you know. I'm very sorry that we haven't been able to be in the same room together to make this class a little easier to teach. Again, please let me know if you have any questions. Please let me know that you have listened to these two videos by giving me the code word of Osaka, O-S-A-K-A. So I will talk with you later, I hope. So I'm going to cut off this recording and then I'll get it converted and uploaded. I hope you have a good weekend, Jessica. And I may talk to you. I'll definitely email you.